All right, well, welcome. I don't know if y'all saw my announcement last night about exams. I finished grading the exams. The scores were okay. In retrospect, I think I might have made the second question on the take-home test a little too hard. So basically, I treated that question as though it were bonus. I gave everybody 10 points for that question, and then any points you did actually earn on that question would count as bonus, essentially. So with all of that factored in, the class average was 68, which is it's not great and it's not terrible. It's pretty normal. 68 to 72 is kind of what I'm used to for class averages on a lot of the tests. And so I went ahead and gave everybody 2 additional points to move the class average to 70. So that's kind of where we stand. The class average ended up with 70. The grades that are listed in Canvas are the grades for the exam. What I'll do is hand back the exams on Monday and go over them with you. I'll go over them pretty fast though. So if you have questions after the fact, feel free to get a hold of me. You'll want to keep your exams on Monday to study with for the final. But we will go over them and I'll hand them back on Monday. So what we want to get accomplished for today is to dive into the Maple side of working with component, composite, phase plots, and systems to make sure that we kind of understand what the different Maple things are here. And then that'll let you start on the homework, which I think you'll be able to do probably 60% of the Maple Lab homework after today, no problem. And then the rest of it will cover harmonic oscillators and SIR models next week. But other than that, I don't think y'all have anything due this weekend, but you should definitely be working toward the things that are due at the end of this module. All right, so let's start with this. This is that rabbit and foxes system that we discussed Monday in class. That was the last example where I showed you the method of using null clines to determine equilibrium points. And I want to go through this example in Maple with you. So you should still have that on your screens. I want to bring up a Maple file. You have access to this Maple file. It's the foxes and rabbits Maple file. So here is how I would recommend you doing any problem that involves systems and analyzing systems. Define each of the equations, so equation 1 and equation 2, and then if you're looking for equilibrium points, remember that you can simply solve a system of equation 1 and equation 2 for the points. So I believe I showed this to you in class on Monday. Or actually it was probably on Wednesday at the beginning of class, but you can use Maple to solve for equilibrium points quite easily for systems. What I want to make sure that you understand is I can't use R of t and F of t if I'm looking for the equilibrium points, but I have to define things in terms of R of t and F of t when entering them as a differential equation. So you can see down here that I have loaded DE tools and that I have to find ODE1 and ODE2 as my 2 equations of my system. So let me go ahead and load those in. And this is the DE plot command. This is the command. Is that better? You said my mic was a little quiet. Is that any better?
Yeah, that's a little better. Thank you.
All right. Sorry about that.
You're good.
So we've defined the 2 differential equations here. So now we're going to do DE plot. If you look at the DE plot command here, you're taking the 2 differential equations and writing them as a system. So you couple them together. And then the vector is the solution that we're looking for, which would be the rabbit foxes vector. You're giving me the ranges of all 3 variables, the independent variable and then the 2 dependent variables. And then there are a host of different options that you can use, right? So you can change the arrows, you can change the color of the slope field or direction field, you can change the color of the solutions that are plotted. And then remember, if you want solutions to show up, you need initial values. So the initial values for a system are initial vectors. And so you enter or input all of the initial vectors for the system inside of square brackets. And finally, I'm going to take the num points option off for a second, just so you can see what will happen if it's not there. Let me go ahead and hit enter and load this up. And what you see is a bunch of different trajectories in the plane that all look like they're cycling toward a point. We'll talk about that in just a second. But what I want you to observe first is the jaggedness of this line. You can see how it goes from here to here, and then it's very jagged to the next point. Because what Maple is doing is it's simply taking the starting point, which the starting point here looks like 4, 1. So that's this initial condition. So the red line here represents the trajectory for this starting vector. All Maple's doing is it's calculating the vector at the start and moving in that direction. And then once it's gone a certain distance in time, it recalculates it and changes the direction that it goes in. Well, that can lead to, if you don't have enough points to calculate for Maple, that can lead to a very jagged looking line. So what you will want to do on a lot of these is increase the number of points. So you can increase the number of points that it's using to calculate. Notice that that smoothed everything out. Or another viable option here is decrease the step size that it uses between calculations. So both of those will have the same effect. So this says every 0.01 in time, recalculate that next slope, right? So that's just dealing with the step sizes that are involved there. So either of those commands is fine. So this actually is a really nice looking graph. I wanted you to see that you can change the colors, make things look nice. I'm gonna do a lot with you today on talking about making your graphs look nice and different things that you can do. But as it stands, we see all of the interesting behavior here. If you go back up to where the equilibrium points are, we've got the 0, 0 equilibrium. You can't really show that one. But notice I've got 0, 3 as an equilibrium point. And if you look, I started out with 1, 0 as an initial point so that it would show that behavior. You can see here the gold line that's at the bottom started at 1, 0 and it approaches 3. That's showing that equilibrium point behavior. That's the logistic growth of rabbits in the absence of foxes. And then all of the other non-zero initial starting points cycle in over time to a single limiting value. And that limiting value turns out to be this non-trivial equilibrium of 1/2 and 5/3. So the place where they're cycling down to is 1 and 1/3. So it's going to be right around here is where all of those points are limiting to. One of the things that you can do to analyze graphs in Maple is up here along the top. If you click on the plot, there's this little spy symbol here, which is really just like allowing you to click and select different objects. But if you click and hold down next to it, if you click the menu next to it, I really like this last one. So if you click that little last option there, it lets you go in and look at any specific values on the graph. So like say I was trying to look at where this graph is cycling down to. I can kind of put the cursor on it and then it's giving me the X and Y coordinates at that point. So it's a good way to sort of investigate behaviors that you see in the graph. I'll go ahead and turn that back to the default, but I just wanted you to be aware that that's something you can do. You can also right click on graphs or click over here on the side and add titles, add a legend and things like that. And I'll do that here in a little bit. But there are lots of things you could do to make the graphs look better. This is a phase portrait of the curve. So we're drawing in the slope field. That's what DE plot does, is it creates slope fields. But as soon as I give it initial conditions, The curves that it draws out are curves in the phase plane. So this is a phase plane plot, which is the solution plot for a system. If I don't want to see the arrows, then I believe I can just say arrows equal none and just get the phase plot. So this is R along the horizontal, F along the vertical, and this is the phase plot for this differential equation, for this system. Okay, what I want to do now is teach you a new optional command. So here's the phase plot for our system. This new optional command is the scene command. So this is a very important command when working with systems, because sometimes instead of seeing the phase plot like I have here, I might just want the component plot. So say I just want to look at what the rabbit population is doing and not look at what the rabbit and fox population are doing simultaneously. The only change I've made to the above input is the scene command. So I'm effectively telling Maple, change my axis to C to be T across time across the horizontal and rabbits R across the vertical. So if I input that, you'll see that these are all of the different behaviors associated with the different initial conditions just for the rabbit population. So this is what we call a component plot. These are very valuable. They tell you a lot about the individual behaviors that are involved. For instance, we saw that this gold curve here was the equilibrium. You can see that this is the carrying capacity logistic growth term for the rabbit population if it started out with 1 with no foxes. And then you can look at the rest of them. This one that starts out at 5, this is R of 0 equal 5, F of 0 equal 1. It's kind of a large F value there. And so that's cratering the rabbit population initially, but it recovers just a little bit and it starts to settle into this cycle. Notice that all of these have some sort of periodicity to them, even though the amplitudes of the waves are decreasing. This periodicity is what's creating the spirals in this plane. So one of the things to maybe jot down in your notes is that spirals or circles in the phase plane correspond to periodicity or waves in the component plane. So component plots that have some sort of periodic wave-like behavior create spirals or cycles in the phase plane behavior. And we'll talk more about that when we talk about harmonic oscillators. I can similarly do the same thing for the foxes. So here are the component plots for the foxes. I can look at all of their individual pieces and compare them side by side. I do want to show you a trick that you can use to make a graph very easily in Maple. Let's suppose that I wanted to create a graph. Make this a little bit smaller here. It's too small. All right, let's suppose that I wanted to create a graph that consists of just the red curves. So just the red curves. I could store a command that says this is plot 1, this is plot 2, and remove all the initial conditions except the ones for the red curves and then display plot 1 and plot 2. But I actually want to show you kind of a little shortcut for that. I'm going to take and highlight this red curve by clicking on it, and then I'm going to drag and pull it down to this open spot. Notice that that just created it just pulled out the red part of that graph and just has it all by itself. I'm going to center it real quick. So this is the part that came from here. Notice it's missing from this plot now because I pulled it out to this new one. I can do the same thing here. I can take from the foxes, drag it down on top of this one, and it'll add it to this one. So now maybe I want to dress this plot up a little bit. So I want to give it a title. So I'm going to add a title. Maybe my title is component plots of T R of T and T F of T for, let's see, what were our values here? The red one that we pulled out is starting at 5. So this is the 5, 1 initial point. So that's the initial point that was used. So for R of 0 equal 5, F of 0 equal 1. So there's my title. I want to differentiate the colors here. I don't want the same color. So I'll just click on one of these. I'll go over here to color and let's just change it to, oh, I don't know, green. Okay, so I've got my 2 different plots. Maybe I want to add a legend. So show legend there. It defaulted to just showing me curve 1, but if I click on the green curve, I believe I should be able to do it for both. Whoops. So click on the green curve, legend, add legend, right? And then red curve, add legend. There we go. So now I got both of them in. Let's see, the red curve here is starting at 5, so that's my rabbits. My green curve is my foxes. I can also go in on the axes and label X and Y. Click on those labels, and this is, let's see, population amounts. And then down here on X, this is time. It could be in months or something like that. The point I want to make is it's very easy to create nice looking graphics. And I think as the semester goes on, you're going to want to invest a little bit of time into your plots just to make them easier for you and I as the grader to read what it is that you're doing. So this is the component plot. This would be what the rabbit and fox population is doing for a specific initial condition. Notice, by the way, that once I've dragged those out onto their own graph, if I go back and re-enter the commands for the previous ones, the red plots show back up. So I can, to me, it's the easiest way if you don't want to create display commands constantly. It's the easiest way to pull out specific components. All right, there is one final command. We talked about the different types of plots in class on Wednesday. We had phase plot, which DE plot, the default for DE plot is a phase plot, which, by the way, if you go back up to this phase plot that we did, I could use the scene command here and do R of T, F of T, and it's not going to change the result because that's the default. The default for DE plot is it's going to show you the phase plot, R versus F. Now, what is sometimes helpful and sometimes interesting is reversing the axes. So I could reverse the axis here and do F versus R. That's certainly possible to do, but normally we will default to component 1, component 2. Finally, the third kind of plot that we discussed in class on Wednesday is something called a composite plot. So remember, the composite plot is sort of needed because if you look at this plot here, time does not factor into this at all. I don't know how quickly the populations are traveling along these trajectories. So I don't know how quick this is happening. If I want to see time involved, I need a third axis. So what you do for this is you'll need to load the plots command, and you'll need to change your DE plot to be DE plot 3D. So I'm going to do a 3-dimensional plot. All of the other commands are the same. So everything else about the DE plot command from earlier is the same. The only change that's made if you want a composite plot is the 3D part of the DE-plot command. So DE-plot 3D. If I go ahead and hit enter on that, you'll see here that you have what all of those different components are doing over time. And so you've got time along this axis, R versus F. I almost always want to orient it this way. In other words, I want to have R and F in the plane and show time moving along the vertical axis. That's usually the best way to look at this. I will tell you the other really interesting way to look at it is to remove time from the problem altogether. And if you do that and look at it, there's our phase plot. So if I orient the three-dimensional graph so that I can't really see the time axis, all I'm staring at there is the phase plot. So this is what the phase is doing over time for this problem. So this kind of analysis is going to be very common on this Maple Lab. In fact, that's what you're mainly practicing on this Maple Lab, is this sort of analysis in a lot of different situations. And it's going to be very common over the rest of the course. So you really need to get comfortable with, in Maple, plotting phase plots, component plots, and composite plots for a given system. All right. So shifting gears a little bit, let's stop talking about rabbits and foxes. I think we've exhausted that particular model. That was a predator-prey model, by the way. So I want to talk about how do our mixing problems that we discussed earlier in the semester, how do they look from a system point of view? So I want to draw the picture with you, and then I'm going to let you tell me which of these is the correct system for it. So you should be able to still see the description of the problem on your device. Let me bring in a little whiteboard here, and let's go over it together. So mixing problem systems. All right, the information given to you here is we have two tanks. So let me draw these two tanks. You've got tank 1. And you have tank 2. And you're told that stuff from tank 1 flows into tank 2. You have things that flow out of tank 2, and then you have things that flow into tank 1. This sort of arrangement for a mixing problem of this type is called cascade. So these are in cascade. By the way, there's a complete analogy here to cascade arrangements of circuits. If you think of each of these as being a circuit connected in this fashion, that's called cascade. The circuits are being done in cascade, which is not that different than being done in series. I do have a circuit question that if we have time to, we're going to look at today, and I kind of want to draw the parallel here for you. So we've got two tanks. We've got this tank at the top that we'll call the upper tank. U of T is the amount of salt in the upper tank. And we have L of T, which is the amount of salt in the lower tank. We're told that pure water flows into the upper tank at a rate of 4 gallons per minute. So pure water would be 0 pounds per gallon. That's pure water, 0 pounds per gallon of salt, flowing in at a rate of 4 gallons per minute. And then leaving the tank, you have a rate of 4 gallons per minute and another rate of 4 gallons per minute leaving the bottom. You're told that initially the tanks are both 100 gallons, so the maximum volume here is 100 gallons, and the upper tank initially has 10 pounds of salt, and the lower tank initially has 20 pounds of salt. All right, so, oh, actually it says that's not the maximum. Well, it actually won't matter. The volume here is 100. We'll talk about that here in a second after you've entered your answers. But this is the setup for the problem. You have tanks that are 100 gallons containing 10 pounds of salt, 20 pounds of salt. All the flow rates are the same. Can you write down a system of differential equations that governs the changing salt amounts in both tanks simultaneously? So go ahead. I've got 4 choices here for you. Tell me which of these is correct. All right, it looks like most of you have responded. I'll give us about another 20 or 30 seconds to finish. All right, all the results are in. So the correct answer here is A. We're a little split here among the class. Let's talk about it. So I'm just going to do the same thing that we did earlier in the semester when looking at mixing problems. The rate of change of salt in the upper tank is going to be the rate at which salt comes in minus the rate at which salt leaves. So salt is coming in at a rate of 0 because there's 0 pounds per gallon coming in. If you want to write it as 0 times 4, you can. And then in terms of what's leaving, it's leaving at a rate of 4 gallons per minute. But what is the concentration that leaves? Well, the concentration that leaves is U pounds. It's leaving at a rate of U pounds per 100 gallons. And the reason that it's 100 gallons is because the rate at which water is flowing in matches the rate at which water is leaving. So if the initial amount of volume is 100 gallons, that is not being changed. So you have U of T divided by 100 gallons leaving times 4. So this would end up being du dt is 0 minus 4 divided by 100 is 25, so U over 25. So that's the upper tank, and this is where U of 0 is 10. So that's the equation for the upper tank. And then if you look, the equation for the lower tank would be, okay, what is coming in to the lower tank? Well, I think we can agree that what is coming into the lower tank is precisely what's leaving the upper tank. So if negative U over 25 is the term that is the rate out of that tank, then that should be the rate into the lower tank. So it should be plus U over 25. So positive rate in to the lower tank. And then if you look at what's leaving the lower tank, it's 4 gallons per minute times L of T pounds per, once again, 100 gallons, because the volume of that lower tank is not changing since the flow rates are identical coming in and leaving. So that should also be 4L over 100, which is, well, I'll just simplify it right there. 4 over 100 is the same as 1 over 25. So this is my system, which is answer choice A. And what I want you to understand is that this is we haven't really seen a system like this. This is what in mathematics we call a partially decoupled system. So the word decoupled is a really important term in applied mathematics, physics, engineering, understanding when a system is coupled versus decoupled versus, in this case, partially decoupled. So partially decoupled means that L, you can look at the variable L, its change depends on U and L. So L is coupled to both of the components in the system, but U is decoupled from L. Notice that the change in U doesn't depend on L. Physically, this essentially is saying that what happens in the upper tank has nothing to do with what happens in the lower tank. But conversely, the lower tank depends on the upper tank. So this is what we mean by partially decoupled. So a cascade arrangement, if you talk about cascade arrangement of a circuit or cascade arrangement of tanks, that corresponds mathematically to what's called partially decoupled systems. I might ask you a question like, what physical arrangement of the tanks would create a coupled system? What would it have to look like in order for this system to be coupled?
If both tanks depended on each other.
Right, so if I had some sort of system where what comes out of L flowed back into U, does that make sense? So if what I had in L somehow flowed back into U, then they would be coupled. And the arrangement of such a tank system would look like this. So you got flow into here, flow into here. Maybe you've got some flow that comes into this tank, and then maybe some flow that leaves over here. So whatever you have here circulates into here, but then it circulates back into here and vice versa. Some leaves, more comes in. This sort of arrangement, if this were my, let's call it left tank and right tank, this sort of arrangement would be what we would call a coupled system. So it's completely coupled. Does anyone know, rather than call this a cascade arrangement like I did here, does anybody know what an arrangement like this would be called physically? If you want to think of them as circuits, it might help you.
Maybe a loop?
A loop is one name you could give to it. It's not the term that we typically use. What if I ran a circuit in parallel? It's the same concept. It's coupled because if you have different components along this part of the circuit, then they would run in parallel with this part of the circuit here. So what goes through here and what goes through here, you run them in parallel processes. So this is actually the mixing version of a parallel circuit process. We say that you're running things in parallel if it looks like this. So the physical interpretation of this in the real world is that you're doing things in parallel. Here, mathematically, we say that you're doing things that are coupled. So you have a coupled system. This can also be realized by saying you're doing things in series. Now for a circuit, series and parallel are not the same, but for a mixing problem like this, you would interpret them similarly. So another question about this particular decoupled system. How would I solve a system like this? Does anybody see a route to solving this that we could do right now? I could completely solve U, right? I could start with this piece here. It doesn't depend on L. And because of that, if I simply solve this piece for U, I can take the solution that I get out of that piece and plug it into the U right here, in which case L, the second equation, would depend only on L. So partially decoupled systems are already solvable. We're already capable of solving those in this course. I do want to show you this in Maple so you can kind of see. I haven't actually answered the question, which is find U of t and L of t. So I want to take a look at this. I do have a Maple file that goes along with this problem. So this Maple file is called Cascade Mixing Problem Example. You can find it in, uploaded on Canvas. So I think I used upper and bottom here. So up and bottom tank, but this is the problem that we just got through looking at. And then here is the general solution for each of these. So that's the upper tank over time, and this is the bottom tank over time. You can see that I've created the phase plot. So this is the phase plot that corresponds to the initial conditions 10 and 20. So the upper tank begins at 10, the bottom tank begins at 20 pounds. Over time, eventually both tanks go to 0. And it should make sense physically that both tanks will eventually have 0 pounds of salt in them, because remember, pure water is flowing into that top tank. So eventually the pure water that's flowing into that top tank is going to wash out all of the salt from both tanks over time. I can then plot the component plots. So these are the components of each. It kind of makes sense that this would be the case. So that should probably be labeled U of t and B of t because it's showing both here. But you've got both the upper tank and the lower tank or bottom tank. Let's see, the upper tank starts at 10, so it's this one right here. And then the lower tank starts here. So the upper tank drains quicker. You can see that because it's going to have the effects from the outside first. The lower tank is going to get some salt from the upper tank, so it's not going to drain as quickly in terms of salt content because it's having salt from the upper tank being added in. So that's why it doesn't drop as steeply as the upper tank does. But eventually both of them run out of salt. You can show the speed using the animate curves equals true option, the speed at which this occurs. So if you take your phase plot and hit play, you can see the speed. In other words, this happens pretty quickly. The initial drop happens really quickly, but then it's very slow from then on. So there'll still be little bits of salt in the tanks that aren't going to get mixed out right away. So you're going to have to go for a while. And then this graph shows you how long that is. This graph is 150 minutes until there's virtually no salt left. So 2.5 hours it would take to wash all the salt out of that system. And then finally, here is the composite plot. The composite plot for this isn't all that valuable. Doesn't really show you a lot. So that's an example of a mixing problem. I want to take a look at a trick that we can use to solve certain systems that turns out to be very valuable for us with this next example. So suppose that we had to try to solve this system. Dx dt is y, dy dt is minus sine of x. This is a nonlinear system because you're looking at the sine of one of the components. That's a nonlinear operation. Maple can't do this. So if you asked Maple what the answer is, this is what Maple would tell you. So desolve x prime equal y prime equal minus sign for initial points x naught, y naught. This is what Maple tells you the solution is. It looks awful. You're not going to get anywhere with that. It turns out that we can be a little bit smarter than Maple here. So the system that we're being asked to look at there is dx dt equal y and dy dt equal minus sine of x. This is a coupled system because x depends on y and y depends on x. So they are coupled, they're linked. Neither of them is decoupled from the other. It turns out that this is the system for a nonlinear pendulum. If we have time later in the course, we'll talk about that. But this is the system for a nonlinear pendulum. What I want to do is divide the two equations. So if I took dx dt and divided it by dy dt, and then take y and divide that by minus sine x, then what you observe over here on the left-hand side is the dt's cancel, which leaves you dx dy is y over minus sine x. Now, why is that significant? What have we managed to do to this system? We managed to turn it into a separable system. So we can actually solve this by hand right here. If I was to go ahead and do a little bit more with it, we've got negative sine x dx would be y dy. If you integrate both sides, the antiderivative of minus sine is cosine. The antiderivative of y is y squared over 2, and I have a constant of integration. So I could just solve for y here, but I'll leave it in this form. Let's just say it's cosine of x minus y squared over 2 equals c. So this would be an implicit solution. The point is, this is a very valuable solution. Implicit solutions are valuable because this is a function in the phase plane. This is a trajectory. This is what gets plotted when we plot a phase plane anyway. So if I could plot this for every different value of c, I would know exactly what the slope field or phase plane looks like for this particular DE. Without having to actually, Maple can't solve the system as it was given, but I know exactly what the phase plane trajectories look like with this little trick of dividing the two equations. And you can see here in Maple, it's exactly what I did. I set up that divided differential equation and solved it. That's what you and I just had on the other screen for the solution. And then I plotted those plots in the using implicit plot, because this is an implicit function. I plotted those for different values of c. And you can see here that this is what the solution looks like. These are all the different trajectories of a pendulum, a nonlinear pendulum under load. You can see here like this trajectory at 2. Think of it as you've got a pendulum that's hanging here, going back and forth. And you're starting at 2, so you pulled it up to here. And as it spins, it comes down, but then it has enough momentum to carry it around and over to the next one. So this is the momentum that carries it around to the next one, and it could cycle back on its equilibrium there. We'll talk more about this system later in the course, but the point I want to make now is I don't need Maple to be able to solve some systems in order to plot their phase portraits myself. I can do that. And then you notice if we just went the DE plot route from the beginning, this is the direction field, and you can see how the direction field matches those trajectories that we came up with. So it's an interesting little trick that for analyzing a lot of systems turns out to be really important. And that is dividing the two system equations and looking at the implicit separable solution of that system as trajectories in the phase plane. All right, so that was a little diversion from what we were heading toward, which is doing some more with these mixing problems. I don't know if you can really see this thing much or not. So here is a mixing problem. You've got this representation of the mixing problem here. The numbers are the flow rates. There are some numbers missing, but those numbers are discussed here in the body of the problem. And what I want you to do, we're going to look at this problem together here in just a second. What I want you to do is tell me which of these terms that we've used as we've started looking at systems, which of these terms apply to the model that we'll create by looking at this mixing problem. So give you a second to think about that. All right, in the interest of time, you've got about 30 seconds. All right, so answers. I'm glad 100% of you said coupled. We just got through talking about that a little bit ago. 44% of you said it's linear. We'll talk about why this is linear. And then good, 67% of you said it's inhomogeneous. So let me take a look at it. I'm gonna actually come up with the system with us here together. If you look at the configuration, we're told that the rate at which things enter, I'll call it R of t, is 5e to the negative t. That's the concentration would be. So this is pounds per liter. So that's pounds per liter of salt that are coming in. The flow rate there, it says in the problem that flow rates are adjusted so that constant volume is maintained. So let's think about, because I've got two missing flow rates, the rate out and the rate in. So let's think about what's happening in X. If I want the volume in X to be maintained, I've got 3 going out and 2 coming in. This needs to have a flow rate of 1. So this would be 1 liter per, what is it, minutes? Hour. 1 liter per hour. So I've got a flow rate of 1 liter per hour coming in from there, 2 coming in from there. So I've got 3 coming in and I have 3 leaving. If you look at Y, I have 1 liter per hour of, it's assumed to be pure water coming in from here. So 1 liter per hour of pure water coming in there. And you've got, what do you got? 3 coming in there. So I've got a total of 4 coming in, 2 leaving there, which means this has to also be 2 here. So the flow rate there is 2 liters per hour as well. And that'll keep all of the volumes for X and Y constant. It's coupled based on the design because X depends on Y and Y depends on X. It's inhomogeneous. So from a physical point of view, an inhomogeneous system is a system that's affected by outside the system. So what I mean by that is if you think about the salt content in tank X and the salt content in tank Y, if it were a homogeneous system, that would say that the only salt in the system comes from tank X and tank Y. There's nothing from outside the system that's being added to X and Y. But here, because you have salt entering at this decaying rate, there is salt from outside tank X and tank Y coming into the system. So that makes it inhomogeneous physically. And I'll show you when I set up the system here real quickly that it's also going to be inhomogeneous from the system point of view as well. So let's think about tank X, the change in tank X. You have 5e to the negative t rate in, but you also have 2 times y in as well. And it says both tanks maintain a volume of 100 liters. So this is the rate at which stuff is coming into tank X. You've got the outside 5e to the negative t times 1 pounds per hour of salt coming in. And then you have the portion from Y coming in as well. That is 2 liters per hour times Y pounds per 100 liters. That's the concentration coming in at a rate of 2 liters per hour from Y. The rate out, so what is leaving tank X, is this bottom piece, which is leaving at a rate of 3 liters per hour. So that would be 3 of X out of 100 liters is leaving per hour. Similarly, if you look at Y, what's coming into Y is what's going out of X. So this part that's leaving X is coming into Y, and you would have 3X over 100. You also have this outer part coming in, but that outer part doesn't contain any salt. So it's just going to contribute 0 to the salt change. So that's what's coming in. And then, what's coming in. And then the amount that's leaving is the 2 to here and 2 to here. So the 2 that was positive inflow here is actually negative inflow over here. So it would be minus 2y there and minus 2y there. So you would end up with minus 4y over 100 that's leaving. Because you're getting 2 over 100 there, 2 over 100 there. So a total of 4 over 100y that's leaving. If you wrote these in a matrix form, this would be xy prime is equal to 2 over 100, no, 3 over 100. So it would be the x component for the first one is negative 3 over 100. The y component is 2 over 100. On the bottom, the x component is 3 over 100. The y component is negative 4 over 100. And then you have this term here, which is all by itself. And that's what makes the system inhomogeneous. So this is the inhomogeneous vector because it tells me what's flowing in from outside the system. Here, it was 0 flowing in from outside the system, so that's why you have a component of 0 in the bottom. So this is what this system would look like in matrix form. And the reason that the system is linear is because the coefficient matrix here does not depend on the components x and y at all. So you have a linear system, linear inhomogeneous system that's coupled. So that would be the correct way to set up this coupled system problem. All right, I know I was working there kind of fast because I know I'm over time. Thank you for sticking with me. Look back at these notes. If you have any questions, feel free to get a hold of me, and you can start doing a lot of the problems that are on the Maple Lab after having seen this. So I'll get back with y'all on Monday, hand out the exams. Have a great weekend. Bye, everybody.
Thank you.
You're welcome.
Bye.
Bye.